Tonight, one of this century's most ambitious projects at the largest reservoir in the nation, which looked like this in 2000. Take a look at what it looks like now. It was so low it could become useless to communities that rely on it. Instead of looking to the sky, engineers are looking miles beneath the surface to get water by essentially pulling the plug of the nation's biggest bathtub.
For decades, the American Southwest lived as if its most important resource could never run out. Millions of people built cities in the desert. Farms stretched across land that would otherwise be almost impossible to cultivate. Highways, suburbs, casinos, factories, and entire economies expanded around one enormous reservoir. But today, that reservoir is telling a very different story. Walk along the exposed shoreline of Lake Mead, and you can see the evidence with your own eyes. A massive pale ring circles the surrounding cliffs, marking where the water used to be. It looks almost like a bathtub that was filled to the top, then slowly drained. Except this is not a bathtub. This is the largest reservoir in the United States. And since the year 2000, its water level has fallen by roughly 160 feet. For the people living downstream, that isn't just an environmental warning. It's an engineering problem. Because hidden hundreds of feet beneath the shrinking surface of Lake Mead is a machine built for a future that once sounded almost impossible. A system designed to keep Las Vegas drawing water, even after the reservoir falls below the level where Hoover Dam can function normally. The price? Roughly $1.5 billion. And the deeper the lake falls, the more important that machine becomes. But there is something even more disturbing. This giant engineering project does not create a single new drop of water. It simply reaches farther down to collect the water that remains. So why did engineers have to build it in the first place? To understand that, we have to go back to the beginning. Nearly a century ago, the Colorado River was one of the biggest obstacles standing between the American Southwest and the cities people wanted to build there. The river could be powerful and unpredictable. Floods could devastate communities, while dry periods could leave the same regions desperate for water. The solution was enormous. Build a dam across Black Canyon. Construction on what would become Hoover Dam began in 1931, during one of the darkest economic periods in American history. Thousands of workers descended into the Nevada desert, where summer temperatures could climb beyond 120 degrees Fahrenheit. They excavated rock. They diverted the Colorado River. They poured millions of cubic yards of concrete. And slowly, an enormous wall began rising from the canyon. When Hoover Dam was completed in 1936, it was unlike anything America had ever built. The dam stood 726 feet high and stretched 1,244 feet across its crest. Behind it, the Colorado River began filling a gigantic basin. Lake Mead was born. At full capacity, the reservoir could hold more than 26 million acre-feet of water, nearly 9 trillion gallons. It became the giant storage tank for an entire region, and the region changed because of it. Las Vegas grew. Phoenix expanded. Southern California developed. Agriculture transformed the desert into one of the most productive farming regions in the country. Hoover Dam also generated enormous amounts of electricity, sending power across Nevada, Arizona, and California. For decades, the system seemed almost unstoppable. Water came in, water went out. The turbines spun, cities grew, farms produced food, and almost everyone made the same assumption. The Colorado River would keep providing. That assumption was the first crack in the system, because the amount of water promised on paper was greater than what the river could reliably provide. In 1922, representatives from 7 states gathered in Santa Fe, New Mexico, to divide the Colorado River. The agreement allocated 7.5 million acre-feet to the upper basin states and another 7.5 million to the lower basin. A later treaty also guaranteed Mexico 1.5 million acre-feet. On paper, the system appeared balanced, but there was a problem hiding inside the numbers. The river measurements used to establish those allocations came from a relatively wet period. Later climate evidence suggested that the long-term average flow was significantly lower. In other words, the system had been built around a river that, on average, did not actually contain enough water to satisfy every promise made about it. For decades, that difference could be hidden because Lake Mead was enormous. Whenever the river delivered less than expected, the reservoir could make up the difference. Think of it like a bank account. If you spend slightly more than you earn, you could survive for a while by withdrawing from your savings. But eventually, the savings account starts getting smaller. That is exactly what happened to Lake Mead. Around the year 2000, the reservoir was still near 1,200 feet above sea level. Then the decline began accelerating. The lake dropped below 1,150 feet, then 1,100, then 1,080, and eventually, the reservoir reached levels that would have seemed almost unimaginable when Hoover Dam was designed. In 2022, Lake Mead reached approximately 1,041 feet above sea level, its lowest level since the reservoir was first filled. Boat ramps were left stranded far from the water. Marinas struggled. Objects that had been underwater for decades began appearing again, and the white mineral bathtub ring became impossible to ignore. That ring wasn't just ugly. It was evidence of how much water had disappeared. But the real danger wasn't simply that the lake looked smaller. The real danger was what happened to Hoover Dam as the water dropped. Hoover Dam doesn't magically pull water from anywhere in the reservoir. Its intake structures were designed around specific water levels. As the lake falls, the amount of water available to those intakes changes. And below certain elevations, the consequences become serious. At around 1,075 feet, a formal shortage is triggered. At lower levels, the cuts become more severe. But then comes a threshold that affects something much larger than water deliveries: electricity. At roughly 1,035 feet, many of Hoover Dam's turbines can no longer operate normally. The generating capacity can fall dramatically. And below approximately 950 feet is what is known as minimum power pool. At that point, the water surface becomes too low for the original turbine intake system to function as intended. Then there's an even more extreme threshold: 895 feet. Dead pool. Below that elevation, Lake Mead would be too low for Hoover Dam to release water downstream through its normal gravity-driven outlet system. The reservoir would still contain water, but that water would effectively be trapped behind the dam. That is what makes the situation so frightening. The danger isn't that Lake Mead suddenly becomes empty. The danger is that it can still contain billions of gallons while becoming increasingly difficult to use. And Las Vegas knew it couldn't simply wait and hope. So engineers began planning for a future in which the lake would continue falling. The answer was buried underground. The original water intake system was designed for a much healthier Lake Mead. But as the waterline retreated, engineers realized that eventually the existing intakes could be left above the surface. So Southern Nevada made a massive decision: build another intake, not near the surface, not at the old waterline, but deep beneath the lake. The project began with an extraordinary challenge. Engineers would have to tunnel beneath an active reservoir. Imagine standing inside a massive boring machine several kilometers underground. There is no sunlight, no open sky, no easy escape route, and above you is an enormous body of water, millions of tons of it. The tunnel eventually stretched approximately 4.7 kilometers. The intake structure itself was enormous, weighing more than 1,200 tons. It was lowered into position at the bottom of the reservoir. The work continued through years of difficult construction, and in 2015, the third intake began operating. But engineers still weren't finished, because even the new intake had a limitation. It shared pumping infrastructure with the older system. So another project was needed: a new low lake level pumping station. This facility was completed in 2020 and became operational in 2022. Its job was simple to describe, but extraordinary to accomplish: move water from a lake that was continuing to fall. The system could move up to hundreds of millions of gallons per day. Together, the new intake and pumping infrastructure were designed to reach water at approximately 875 feet above sea level. Remember that number: 875. because the dead pool elevation is about 895 feet. That means Las Vegas built a system capable of reaching water roughly 20 feet below the level at which Hoover Dam itself would no longer be able to release water downstream normally. Think about what that means. The reservoir could fall into a condition where Hoover Dam could no longer deliver water through its traditional system. The turbines could stop producing power. Downstream deliveries could face catastrophic consequences. And yet Las Vegas could still reach water sitting below that threshold. That is the extraordinary part of this $1.5 billion engineering lifeline. It wasn't built because the city discovered a secret source of water. It was built because engineers understood that the water was disappearing. So they built a way to follow it downward. And that distinction matters, because the project solves one problem. It does not solve the larger one. Las Vegas still has to conserve. And this is where the city has done something unusual. For a place famous for fountains, resorts, golf courses, and enormous buildings in the middle of the desert, Southern Nevada has spent decades trying to reduce the amount of water it consumes. One of the biggest targets was grass. Decorative lawns require enormous amounts of irrigation in a desert environment. So homeowners were paid to remove unnecessary grass and replace it with desert landscaping. Since the late 1990s, hundreds of millions of square feet of grass have been removed. The savings have been enormous. Southern Nevada has also invested heavily in recycling. Indoor water doesn't necessarily disappear forever. Water used inside homes and buildings can be treated and returned to the system, allowing the region to receive credit for water sent back to Lake Mead. And the results are striking. Despite adding hundreds of thousands of residents, Southern Nevada dramatically reduced its per-person water consumption. The city was growing, but its water use per person was falling. That is one of the reasons Las Vegas has been able to prepare more aggressively than many communities around the Colorado River. But there is another reserve most people never see: underground storage. Water can be placed into aquifers and held there for future use. It's essentially a savings account beneath the desert. Together, these strategies represent a remarkable level of preparation. Conserve water, recycle water, store water, and when necessary, drill deeper for water. But none of those strategies change the Colorado River itself. The river is still being squeezed by drought, increasing temperatures, shrinking snowpack, evaporation, and decades of legal commitments that assumed more water would be available than the river can reliably provide. And that is where the story becomes bigger than Las Vegas. Because Lake Mead isn't an isolated reservoir. It is one piece of an enormous system. Snow falls in the Rocky Mountains. That snow melts. The runoff feeds the Colorado River. Water is stored in reservoirs such as Lake Powell. Then it moves downstream toward Lake Mead. If the upper basin receives less snow, the consequences eventually travel hundreds of miles. And in recent years, that chain has become increasingly fragile. The problem isn't simply one bad winter. The region has experienced a prolonged period of severe drought. Warmer conditions can increase evaporation. Dry soil can absorb more precipitation before it becomes runoff. Snowpack can shrink, and the river can deliver less water, even when snowfall doesn't look catastrophic at first glance. Meanwhile, millions of people continue depending on the same system. Farmers need water. Cities need water. Tribal communities need water. Industries need water. Power systems need water. And every state has legal claims that are extremely difficult to change. That creates a problem no tunnel can solve. If there is less water, someone has to use less. The engineering can move the water. It can store the water. It can reach deeper water. It can make turbines work at lower levels. But it cannot manufacture a new Colorado River. And that is why the future of Lake Mead may ultimately depend less on what engineers can build and more on what people are willing to give up. The warning signs are already visible. The bathtub ring remains exposed along the cliffs. The reservoir is dramatically smaller than it was during its healthiest years. Hoover Dam produces less power than it once did. Farmers have already faced cuts, and the states that depend on the Colorado River continue struggling to agree on how to divide a shrinking supply. At the same time, engineers are still trying to adapt. New turbine technology is being developed for Hoover Dam to keep generating electricity at lower lake levels. The idea is remarkable. Instead of accepting that the falling reservoir will eventually shut down the original turbines, engineers are redesigning the machinery to operate under conditions the original designers never expected. Again, the pattern is the same. The lake falls. Engineering moves the boundary. The lake falls farther. Engineering moves it again. But eventually, there's a limit. And that is the question hanging over the entire Southwest. How far can engineering push back against a disappearing resource? Las Vegas has spent billions preparing for a future in which Lake Mead is much lower. It has removed grass, recycled water, stored water underground, built a massive intake beneath the reservoir, constructed pumping infrastructure capable of reaching extremely low elevations. And now engineers are working on ways to keep Hoover Dam generating power at levels that once would have threatened its turbines. It is an incredible demonstration of what engineering can accomplish, but may also be a warning, because the more sophisticated the system becomes, the easier it is to forget what the system is really telling us. The machines aren't defeating the drought. They're adapting to it. They're buying time. And every foot the lake loses makes that time more valuable. Somewhere beneath the surface of Lake Mead, the 1.5 billion intake waits in the darkness, ready to reach water that older infrastructure can no longer access. Above it, the bathtub ring remains on the cliffs, a permanent line separating what the Southwest once had from what it has now. And perhaps that is the most unsettling image of all. The engineers have built a lifeline. They have built machines capable of chasing the water downward. But eventually, the question won't be how deep engineers can go. It will be how much water the Southwest is willing to live without. Because Lake Mead was never supposed to be an endless supply. It was a reservoir, a storage account. And for decades, the American Southwest spent from that account as if the balance could never reach zero. Now the balance is visible on the walls. And the next chapter will determine whether engineering can keep the system alive long enough for the people who depend on it to change the way they use the river. The 1.5 billion lifeline may have bought Las Vegas more time. But time is not water. And eventually, the entire Southwest will have to answer the same question. What happens when there is simply less to divide?